Hello, this is Mr. Sorrentino again, presenting you another video in this Math 31 series of lectures. And this one is going into 4.3, which deals with polynomial division, the remainder theorem, and factor theorem. Ultimately, one of the main things we're trying to do in this chapter 4 is come up with methods of helping you solve polynomial equations, namely finding the zeros of polynomials. Because if you solve it, if you change any equation that's a polynomial equation and set it equal to 0, that's all you need to do to solve any polynomial equation. We looked at some graphing things that helps us like kind of get an idea what the graphs look like, which could help us identify where zeros may or may not be. And so we've looked at those techniques, but there are still some things that were missing from it, and then that, even when we did an example of a graph in the previous video, although it was very close, it wasn't, as accurate because, as I noted on that graph, I kind of had it drawn with the minimum occurring at 0, -8, and that's not where the minimum actually was. So there might be more things we need to look at as we do this to help determine what the shape looks like and come up with an accurate graph. But ultimately, to do that, we're going to have to find ways of factoring polynomial expressions to find those zeros. And although in certain formats we can do that quite easily, in others it's not as easy. So we're going to look at methods here of helping to identify and determine where factors and therefore zeros may be, and use that and add that to the techniques we've used so far to come up with better graphs and come up with solutions to these polynomial equations and functions. And one of the things that we can make use of for this is the factor theorem. And what this factor theorem allows us to do is if we're able to somehow identify the zero of a polynomial, then knowing a zero helps us know what a factor is and vice versa. Because for a polynomial f of x, if f of c is 0, then x minus c is a factor of f of x. So that means if I'm able to use some technique of determining what the zeros of a polynomial are, I then know what the factor is. So for instance, when I look at f of x equaling x squared minus 6x plus 5 as it is in part A here, we have methods of factoring this. I'm going to use the AC method on this being A, the -6 being B, and the plus 5 being C. Because I notice here, because if I do AC, that equals a positive 5, and there's not a whole lot of factors that can come out and give you positive 5. As a matter of fact, there's only two. I could have 1 times 5, or I could have -1 times -5. And so, as we can see here, it's a -1 and -5 that when added together give me that -6. So I want to think of, doing this is that f of x would equal x squared minus x minus 5x plus 5. And then I could do a group and factor from there, grouping these two together and grouping these two together. And I can say, well, factoring an x out of the first group gives me an x minus 1. And if I factor a -5 out of the second group, I get an x minus 1, which in turn, since both of them have this multiplication in it, I can factor that out. And what's left when I do that, because these would go away, is x minus 5. So that's a basic factoring technique that we looked at before when we were factoring quadratics. But factoring, remember, doesn't always work. It only works when we have rational zeros. The fact of the matter is, just because I may have a situation where they're not rational doesn't mean I can't do this. So for instance, if I tried the AC method on this, and I'll just show it really briefly, kind of up here. If I start with the AC method on part B, I have a 1 here, I would end up with 4. And the only ways I can get 4 are 1 times 4, 2 times 2, negative 1 times negative 4, and negative 2 times negative 2. None of those will add up to give me a minus 6, which is what b equals. Therefore, I cannot use factoring, quote unquote, as a way of dealing with this. But I would need to come up with some means of maybe factoring this to find out what the answers are. So if I wanted to, and if I could, since this is quadratic, I do have other methods of solving this if it's set equal to 0. I can find the 0 and then just simply use this rule to make it a factor. So let's apply the quadratic formula. Because now if I set it equal to 0 and find the zeros, I can say, well, x is going to equal 6 plus or minus the square root of negative 6 squared, which is 36, minus 4 times 1 times 4 all over 2 times 1. I end up with the square root of 20 in here. The square root of 20 can be simplified or split up into square root of 4 times square root of 5, with the square root of 4 being the largest perfect square that goes into 20. And therefore, I would end up with 6 plus or minus 2 square root 5, all divided by 2. And if I divide by 2, remembering to distribute, I'm going to have 3 plus or minus the square root of 5, are my zeros. So my zeros are x equals 3 minus the square root of 5, and x equals 3 plus the square root of 5. Those are my zeros. These are zeros. Which means to find factors that would give me the x squared minus 6x plus 4, and let me scooch this up a little bit, all I really have to do is slap some x minuses in front of them. So the factors for b would be x minus 3 minus square root 5 and x minus 3 plus square root 5. And if I simplify these a bit by getting, I don't like having parentheses inside parentheses, I could rewrite this and now say, well, f of x factored is x minus 3 plus square root 5 times x minus 3 minus square root 5. And so what I would have, this is almost written as a trinomial because, I'm looking at 3 plus square root 5 as a single number, but I'm writing it as a rational and irrational term combined. So this would be a way of factoring it that I wouldn't really be able to come up with using techniques from before. I could do the same thing with C. If I determine what some of the zeros are, I could easily figure out, how to factor it. It gets kind of hard to do because we haven't talked about some of the other things we have at our disposal that we're going to talk about in this lesson. So for the time being, I might have to use another method. And we've talked about other methods before. And one of the methods that we always try out is that if I have an even number of terms, which I do, I have 4 separate terms here, I could try a group and factor. I split these into 2 equal groups, and I look to factor the first group. So what will come out of the first group? It looks like basically an x will come out of the first group. Or no, an x squared. I kind of put over the parenthesis over the 1 squared. So I can factor out an x squared out of the first group and ended up with 4x minus 3. And then I can factor out a -3 out of the second group, we end up with 4x minus 3 as well. When I do a group and factor, I'm hoping that when I factor both groups, I end up with the same thing left in parentheses. It's not a guarantee. And so don't force it to happen if it's not meant to happen. It just means that this method won't work and we have to go on to something else. So sometimes you will try this and it will not work, and you'll have to resort to using another technique that we're going to talk about as we go through this lesson. So as a result, f of x can be rewritten as 4x minus 3 times x squared minus 3. Now that's factored, and if it's factored into linears and quadratics, we're typically happy. But if we wanted to factor this even further, I could say, okay, well, with this information and set this equal to 0, I can find the zeros. And the zeros of this polynomial would be occurring when 4x minus 3 equals 0, or x squared minus 3 equals 0. And if I solve both of these, this one here, I'm going to add 3 to both sides, divide both sides by 4. I get x equals 3/4. And on this side here, if I take x squared, I get 3, which means x is going to be plus or minus the square root of 3. So my zeros are x equals 3/4 square root 3 and negative square root 3. If I want to write this in a new factored format, say I have f of x equals, well, the 4x minus 3, as we saw here, is what gave us the x equals 3/4. So me rewriting the 4x minus 3 is the factor that gave that to us. The other two factors I can write, though, are going to be x minus square root 3, just putting an x minus in front of that, and x minus a negative square root 3, which of course is going to become a plus square root 3 if I simplify it further. And if I would take the time to go through and use the distributive property on this, I would get back the original function. As I said before, factoring it completely into linear functions is not always going to be necessary for our purposes. As a matter of fact, most of the time we're not going to do it. This would be suitable enough because we have methods of dealing with linear equations as well as quadratic equations. So as long as we are able to split a function into linear and quadratic parts, we're good. We don't necessarily have to go and make everything linear parts to do it. Factoring, though, it could be a little bit daunting because sometimes it's not as easy as using a group and factor. You may have to try and put some numbers in and see if they become zeros and factor that way. So we're going to talk about some ways of, once we establish that and maybe the grouping and factoring doesn't work, well, how would I get this factored? If I look at a function and I say I figure out that x minus 3 is a factor, and the grouping and factor doesn't work for that, how do I find other factors? How do I, factor that x minus 3 out? Because we really don't have a procedure for doing that if we can't use a group and factor and if we don't have quadratics to do it. So let's see how we would go about doing that. One way of factoring something out of, like a polynomial expression out of another, is to do long division. So let's look at long division first. So long division is aptly named. It is a long process. And you're going to see that as we go through and do this. But before we get into doing this for polynomial functions, let's review long division from your good old elementary school days where you learned how to do that. Let's do a division over here. Say I wanted to divide, I'm just going to come up with some random numbers, 64, 71, and I want to divide it by 58. Pretty standard thing that you have to sometimes handle when you do this. Let's go back and talk about how we used to do this long division. Well, we always had the first number, the one that's being divided, go underneath of this bracket. It looks kind of like a square root symbol. Some people actually start using square root symbols for this. It isn't. But, you know, we use this. And the 58 would come out here. The next thing we do is we would start with the very first term and say, okay, well, how many times could 58 go into that first term? Well, since this is a two-digit number out here, 58 is not going to go into 6. So with the first term, if that's the case, then I would then look at the first two terms and say, okay, well, how many times does 58 go into 64? Well, 58 times 1 is 58. 58 times 2 is 116. That's way too big. So it seems as though 58 is going to go into 64 one time. So do 1 times 58 and get 58. I would subtract what was here. 64 minus 58 is 6. And once I got a number here, I would bring down the next term, 67. 58 does go into 67. Again, since 58 times 2 is 116, that's too big. It's going to go in once again. And 1 times 58 is 58. When I subtract these now, I get a 9 here. I bring down the 1. Now, I picked one. I was just picking one just to show the review the process. So obviously we have different numbers than ones than this, but this one here just happened to be that all were ones, because again, 58 times 2 is 116. That's way too big. And when I subtract this, I would end up getting 33. Now, after this point, what I would typically do is carry through. I'd either say take this as a remainder. I would, or I would go and say, okay, I would do 1, 1, 1 and 33 58ths, and if I could simplify that, which I don't think I can, yeah, 3, 11, 2, and 29 don't have any common factors, so that would not simplify. Or the other thing you could possibly do when you had numbers is you would say, okay, I'm going to put a decimal point here and here, put a 0 here, drop that down here, and keep going with this until I either find a repeating pattern or it would terminate along the way. So I could sit here and say now, 330, and say, well, 116 will certainly go into that now. I could try 3 times 58 and 4 times 58 and see what would possibly work with that, and keep going with this. The remainder part is good for our purposes here, because when we do these divisions eventually, you're not going to be given any problems where you're just asked to do the long division. You're asked to do the other type of division we're going to talk about momentarily. You're going to do the division for the sole purpose of factoring. You're not going to do it for any other reason. So you're not going to get situations where there's remainders, because you're going to be using it for a very specific purpose. We're going to talk about remainders momentarily, but we're not going to really focus our attention on what the remainders are and how we get to those. We want to focus our attention on the ones where we have no remainders, and there's ways we can figure that out. How does this work with a polynomial? Well, when I set up the long division for this, what comes first, much like this, is going to go underneath the long division sign. So the 4x cubed plus 10x squared plus. Now, one of the first things you have to realize, we're always going to have these written in standard. We're always going to have these written in standard form. So keep in mind that, first of all, the expressions will be written in standard form, which means that if it's not written in a way where any of the expressions are going from highest power of x to lowest power of x, I'm going to change that. I'm going to make sure they're put in that order. The second thing I'm going to make sure I do is missing terms will be represented with 0 coefficients. And so what that means is, when I look at this expression so far, I have 4x cubed plus 10x squared. I don't have an x term. So I'm going to place that with a 0x, then a plus 9. This is the exact same thing. Typically, we don't write it with the 0x there. We would just simply ignore it. We need this for the placeholder because the position, the x cubed, x squared, x, and constant term are kind of describing that they're taking the places of the place value of the numbers. So if I don't have any x term, I need to signify that with a 0. Works the same way with the number out here. Out here I have 2x squared. I don't have a 0 term, but I have a minus 5. So I write it the same way, and if there's any missing terms, I put 0 coefficients in their place. I know since there's 3 terms out here, I'm going to be going 3 terms at a time. But I'm only mainly concerned about the first terms. So as a side problem here, I want to say, okay, well, 2x squared times what is going to give me a 4x cubed? Well, for the coefficient, I'd have to multiply that by 2 to get the x squared to become an x to the third. I'd have to take x squared times x. So I know that I had to multiply 2x squared out here by 2x to get the 4x cubed. I want that to match up. So I'm going to multiply by 2. I'm going to indicate a 2x up here. And then I'm going to multiply this entire thing by that 2x. 2x times 2x squared is 4x cubed. I wanted that to happen. I wanted that first term. It's always my desire to make the first term match. The other ones, if they match, so be it. If they don't, oh well. 2x times 0x would give me a 0 for coefficient x squared. Now again, under most normal circumstances, I wouldn't have had the 0x there to begin with, and even if I did, if I had up with 0x squared, I would tend to ignore it. But I'm not doing that here. I got to make sure to keep the places in line. 2x times a negative 5 is a minus 10x. Now, just like before, over here, I'm going to subtract. Now the thing is, I'm not subtracting a number here. I'm subtracting an expression. So I'm subtracting this entire quantity, which means I have to distribute. So we usually don't write the parentheses there, mind you. Just when I put the subtraction in, I have to make sure that each term is being distributed. So basically that means that every term is going to have a sign change. So this becomes a minus, this becomes a plus. 4x cubed minus 4x cubed cancels. The first terms should cancel if you're doing this right. If other terms cancel as well, great. If they don't, that's okay. 10x squared minus 0x squared is 10x squared. 0x plus 10x is 10x. And then I bring down the next term like I had done with the other division, with the numbers. So I'm going to bring down to plus 9. Now I'm focusing my attention on this new first term. And I'm going to ask myself the question, 2x squared times what gives me 10x squared? Well, we know that there's no change in the exponent, so I'm not multiplying by anything that has an x in it. Therefore, the only thing that's going to change is the coefficient, and 2 times 5 equals 10. So 2x squared times 5 would be 10x squared, which means I'm going to multiply this now by a positive 5. And since it's the second term, I have to indicate positiveness by a plus sign. And so I'm going to get that 10x squared. 5 times 0x is 0x still. 5 times negative 5 is a minus 45. I would subtract. Again, when I subtract, it has to be distributed, so that's going to become a minus. This is going to become a minus. This is going to become a plus. These cancel, they should. 10x minus 0x is 10x. 9 plus 45 is 54. So I could just state like the answer is 2x plus 5 and the remainder is 10x plus 54. This one wasn't too bad because we started with an x cubed term. We were dividing by an x squared expression. The bigger the discrepancy between the two, the more work there would be when I do long division. So here, I had to do two different steps to do this long division, an x cubed expression and dividing by an x squared expression. In the next one, I'm taking an x cubed expression and dividing it by an x expression. So I have a degree 3 polynomial expression being divided by a degree 1 polynomial expression. And here I'm going to do, again, the expression that comes first is what goes underneath here. Now here I don't have any missing terms. I have an x squared and x, x cubed and x squared and x in a constant term, so everything there is good. And I have the x plus 3 out here, again, no missing terms. I focus my attention on the first terms. And I have to ask myself, okay, x times what equals 2x cubed? Well, I went from having a coefficient of 1 to a coefficient of 2. So that means I had to multiply this by 2. I went from an x to the first power to an x cubed, so I had to multiply this by x squared. So for me to have that all happen, I had to multiply x plus 3 by 2x squared to get a 2x cubed in the same first position. So I'm going to carry through, I'm going to multiply 2x squared to x plus 3. It's distributive again. So I'm going to have 2x cubed plus 6x squared. And I have to remember now that I'm going to carry through the subtraction, so I'm going to subtract, but that subtraction gets distributed, so this becomes a minus as well. These cancel. Negative 2x squared minus 6x squared becomes a minus 8x squared. And I bring down the next term, which is a minus 7x. And now I focus my attention on this new first term. And so I have now x times what would give me a minus 8x squared. Stands to reason negative 8 should be part of that. To have x to the first become an x squared, it had to be multiplied by x. So I had to multiply this x outside by a minus 8x. And so I'm going to have a negative 8x squared minus 24x. Again, I'm going to carry through the subtraction. Since I'm going to be subtracting, this becomes a plus because it's going to have a sign change, minus a negative, and same thing with this. These cancel. Negative 7x plus 24x becomes 17x. And I bring down the 15. Now, when I do this now, it's going to be my last one. I'm going to have a remainder after this. So again, my new first term is 17x. I think again, well, x to the first power times what gives me 17x technically to the first power. Well, the powers remain the same, so there was no x in whatever I multiplied it by. I just had to make the coefficient go from a 1 to a 17, so I know I had to multiply this by a positive 17. That's an ugly x I had up there. Plus 17. And so I'm going to have up 17x here plus 17 times 3 is 51. I carry through my subtraction. These cancel. This is a minus now. 15 minus 51 becomes a minus 36. And that's what the remainder is. So I end up, so if I divide, I'm going to end up with 2x squared minus 8x plus 17 with a remainder of negative 36, which is kind of different because long division with numbers, we didn't have negative remainders. Here we're going to, and that's, that's another new thing about this. That was kind of lengthy. Now, if I had had a situation where I had like a 6th degree polynomial expression being divided by a 1st degree one, that'd be even more steps. None of them particularly difficult, but just time consuming. So, and it's this kind of division where I'm dividing by what we call here a linear binomial with a leading coefficient of 1. That's going to be the circumstance that whenever I start wanting to factor these polynomial functions that I'm going to have, because chances are I'm going to probably be able to find a 0 or 2, change them into a factor by putting an x minus in front of them, and therefore I'm going to have x minus some number or x plus some number because I had x minus a negative. And then, that's what I'm trying to divide out and see what I have left to possibly factor some more. So this is the kind of situation I'm going to be happen most often because, of the rule we had before about how to use the factor theorem. So this, being so time consuming could be a problem when I'm trying to do this rather quickly. So we have another method of carrying through this division. And you're going to see we're going to get the exact same answer and result that we would do if we're doing the long division. So let's have a look at synthetic division. Now notice in example 3, I have this exact same thing as I did in example 2, part B. But here's what's different about it. I'm going to take what's inside the first quantity, the first expression, the one with the higher degree. And all I'm going to do is write the coefficients. So these, gotta switch back to my pen, these are the coefficients of the dividends, which I think they officially call the number being divided. So, I have a 2, minus 7, and positive 15 here. That's what I have here. This number is the 0 of the divisor. Since x plus 3 is the expression, I got to think, well, what number would make that a 0? Well, negative 3 would. So that's what goes here. And then once I have this set up, how I carry this through is as follows. I start with this number up here, I bring it down below the line and just say 2. To create a new number that goes right here, I'm going to multiply the negative 3 I have in this half box to the left, upper left, times this 2. So I'm going to do negative 3 times 2 and get a minus 6. I'm going to now, and here's what's another major difference, I'm going to add these two together. So negative 2 plus negative 6 is a negative 8. Once I get a new number down here, I'm going to now multiply that by the negative 3 up here. I'm going to get a plus 24. I really don't need to put a plus sign there, but I am going to add the numbers together, which gives me a positive 17. With the new number down here now, I'm going to take the 17 times negative 3. I'm going to get a minus 51. And when I subtract, I'm going to get a negative 36. The number that ends up in here is the remainder. As I work my way this way, this is my x to the 0 term, or my constant term. This is my x to the first term. This is my x squared term. If I had more, it'd be the x cubed term, the x to the fourth term. So based off of this, the answer is 2x squared minus 8x plus 17 with a remainder of negative 36. And as you can see, that does work a bit faster than the long division did. Again, synthetic division only works when you are working with a linear binomial, and I'm going to make sure to emphasize here, and leading coefficient of 1. It gets a little bit more complicated if you don't have that. So, that's a shortcut. Now again, we're not going to be using this synthetic division for just doing division. You're not going to say, hey, divide this. You may have some practice problems in your textbook just to get you used to the procedure, but ultimately the goal is not to use synthetic division just to divide two polynomials. It's going to be used once you know that the remainder is going to be 0. You just want to use it to break down the function more. So if you're able to establish a 0, then you could turn that into a factor, carry through the division, and then you have it broken down into that factor times whatever's left over when you carry through the division. For this to be useful as well, we're going to talk about now the remainder theorem. So let's talk about the remainder theorem and what that tells us. So we're going to do an exploration of the remainder theorem. And I'm going to be doing these using synthetic division just for the time being, because we're going to hopefully notice something that goes on with this. We know that f of x is being defined here as x squared minus 6x plus 7. So in the first one, I want to do f of x divided by x minus 7, which means that for a, I'm going to be taking the function f of x, which has coefficients 1, negative 6, and 7, and I'm going to divide that by a 7, because that's what the 0 would be for that factor. And I'm just going to carry through the synthetic division here. So, and I'm not going to do this, I'm not doing it in fast motion here because this gives us an opportunity to practice more synthetic division. So as I carry this through, bring down the 1, multiply that by 7, I get 7. Negative 6 plus 7 becomes a 1. That should be a minus 7 up here. 1 times 7 is 7, and I get a remainder of 0. So the answer to this is, so this is basically telling me I have a remainder of 0, and this is my constant term. It's a constant. This is my x term. So this division is equal to x plus 1 with the remainder of 0. When I do b and do f of x divided by x plus 2, I'm still going to have the 1, the negative 6, and the negative 7. Since x plus 2 is the factor, the 0 that would result from that is a negative 2. And so if I carry this through, bring down the 1, multiply by negative 2, I get negative 2. Add those together, I get a negative 8. Multiply that by negative 2, I get a 16. Negative 7 plus 16 is 9. This is my remainder. This is my constant term. This is my x term. And so that means when I carry this through, I end up with x minus 8 and a remainder of 9. But let's see what happens now. What if I just did f of 7? Notice that 7 is the 0 that becomes this factor. If I do f of 7, I'm going to have 7 squared minus 6 times 7 minus 7, which is 49, minus 42 minus 7, which equals 0. That seems to be the same remainder. And it stands to reason. If 7 is a zero of this polynomial, by the factor theorem, I would expect x minus 7 to be a factor. And if it's a factor, and I carry the division through, for it to be a factor, I get a remainder of 0. Going back to numbers, 2 is a factor of 12. How do I know? When I do 12 divided by 2, I get 6 with no remainder. So that's how I know it's a factor. Here, again, this negative 2 is the root I would get from this factor. So there's a relationship between this. This is the factor for this 0. What happens when I do f of negative 2? Well, if I plug that into the function, I'm going to have negative 2 squared minus 6 times negative 2 minus 7. That's 4 plus 12 minus 7. And 4 plus 12 is 16, minus 7 is 9. It matches yet again. So I don't have to carry through a division to figure out what the remainder is going to be when all is said and done, as long as we're talking about linear binomials with a leading coefficient of 1. And that's what the remainder theorem has you notice, and that's what it basically states. Given a polynomial f of x and the division of f of x divided by x minus a. X minus a, of course, binomial, 2 terms, linear because x has a power of 1, leading coefficient is 1. Has a remainder r if and only if f of a equals r. So basically, if I want to figure out what the remainder is, all I have to do is plug in the number, the potential 0 I'm going to have from the factor, and it's going to tell me what the remainder is. That works for these linear binomials, and that's the whole reason why the factor theorem works. A 0 of a polynomial is going to be it's going to help me figure out what a factor of the polynomial expression is going to be. So these two working together is what allows us to, well, if I can find some zeros, that helps me factor, and it might help me find other zeros. Because even though we may have a graph in front of us, that graph, might not give us the exact value of irrational factors. I mean, if I even use my calculator, I might get some decimal. It's an approximation. If there's some non-real factors or non-real zeros, they won't even show up on the graph. And I need to be able to find those too, and I'm expected to know how to find those as well. So that's what we're going to start looking into. How are we going to do this type of thing? Let's look at example 4. Now this is kind of getting into a situation where I'm using the calculator. I really don't have to use the calculator on this. If you look, you could use a group and factor method of factoring this and breaking this down in much the same way. I'm setting it up this way so that you can see how the calculator could be useful in identifying some zeros, and 2, how it's going to help me, eventually get the exact values of some of the other zeros. Now I'm not going to show this all in the calculator because I have pictures that are from the notes in here as well. So here you're asked to find all the zeros, and you're asked to find exact values. That exact values is very important because, if I just said find the values of the polynomial, you could, potentially find the answer to this just by graphing it and using your trace functions and things of that nature. So what you're seeing here is this is a graph of y equals x cubed plus 2x squared minus 10x minus 20. And you can see what the settings were for us to see what we have here. As you can see, this graph does show 3 zeros. And that's how many zeros I expect. I don't expect any more. Because I'm already seeing those 3 zeros, because the end behavior should have this pointing left on the left, pointing down on the left-hand side and pointing up on the right-hand side, I know I'm having a sufficient graph here to determine with that I have all my zeros in front of me. So I'm using those facts that we've mentioned in previous lessons to establish that yes, these are the only zeros I expect to see. Now if I'm using the calculate menu, I find out, as this mentions here, this is my x equals -2. This number here is -3.1627776, and that's rounding. There's no repeating pattern to this, and it doesn't just terminate. Usually termination, you're going to see like -3.25, bam, done. Or you might see it as -3.24999999. So it indicates that you would normally just round to 3.25. This number here, the way it's coming up on my calculator when I use the calculate menu, indicates that this is irrational. Same thing with this. It's just a positive version of this, which stands to reason we talked about before that irrational roots or zeros tend to come in pairs. The problem is, if these are irrational and I have these decimals, this is not the exact solution. That's what this wavy equals sign means. It means approximately equal to. I don't want approximately equal to. I want exactly equal to. So I got to try to figure out what this number is written in exact form. And the only way I'm going to be able to do that is to break this down and try to solve this situation. So I am solving a situation where this is set equal to 0. I know from this that x equals -2 is a 0, which implies that x minus -2, which of course is the same thing as x plus 2, is a factor. Since I know it's a factor, I should be able to divide it out, get another expression, that's the quotient, that has a remainder of 0. So essentially, I'm doing this synthetic division now to factor this. Because right now it's a cubic function. I don't have methods of solving this equation for cubics. But if I can break this down into factor out this linear factor, I'd end up with a quadratic one as well, and I can solve quadratics. I can find zeros for quadratic expressions. I can't find them for cubics. So I'm going to carry through the synthetic division now. So again, the synthetic division, I have it set up so, here's my coefficient of 1, which goes with the x cubed, the 2, which goes with the 2x squared, the -10 goes with the -10x, the -20 that goes with the -20. And of course, in synthetic division, I use the 0, not the factor, so that is a -2. So I do the synthetic division. I bring down the 1. Multiply that by -2, I get -2. I add the two numbers together, I get a 0. -2 times 0 is 0. Add those together, I get a -10. Now I multiply the -10 times -2, I get a +20. And I get a remainder of 0. Good, I should get a remainder of 0. This is my constant term, this is my x term, this is my x squared term. So obviously when I rewrite this, I don't have to write the 0x. I can get rid of that as part of my solution. So now I know that f of x, originally written like this, can be rewritten as x plus 2, because that's what gave me the -2 as a 0, times x squared minus 10. And I'm trying to set that equal to 0. The zeros, therefore, well, we already established that -2 was a zero, but if I go through the process I normally do at this stage, I'm going to say, well, x plus 2 would have to equal 0, or x squared minus 10 would have to equal 0. Well, if x plus 2 equals 0, we get that x equals -2. That's not a shocker because we've established that much earlier in this problem with the calculator. Or I could have even established that using group and factor. The x squared minus 10, this is going to be what generates that 3.16 something or other, and the negative 3.16 something or other, because I'm going to add 10 to both sides, and then I'm going to square root both sides. Remembering the plus or minus sign goes there. So I'm going to end up with x equals plus or minus the square root of 10. Those are my other two, because remember, one's the positive one, the other one's the negative one. So my zeros are, I could do them as a list. I could say it's -2, square root 10, and negative square root 10. Those are the zeros of my polynomial. In section 4.4, theorems about zeros of polynomial functions. Here is where we're kind of putting every little piece together about polynomial functions in order to find any and all zeros of the polynomial function. So we're going to present a few more rules that we're going to use in conjunction with the other rules that we looked at, so that we can accurately and completely find exact values of every single zero of a polynomial function. Some rules that we're going to be talking about here is that the fundamental theorem of algebra basically says that every polynomial of degree n, with n being greater than or equal to 1, has at least one zero in the set of complex numbers. So basically the fundamental theorem of algebra kind of boils down again that the degree of the polynomial should dictate how many zeros that polynomial has, and that you need to account for that many. So if I know if it's a fifth degree polynomial, I need to account for 5 zeros. If it's a seventh degree polynomial, I need to account for 7 zeros, so forth and so on. Non-real zeros. If a complex number a plus bi is a zero of a polynomial f of x with real coefficients, then its conjugate is also a zero of f of x. Basically what that's telling you is that non-real zeros come in pairs. And that's basically as a result of the quadratic formula again. This also works when I'm talking about rational roots or zeros, a polynomial with rational coefficients. If I have a polynomial with rational coefficients, so they have to be not just real, they have to be rational. If a plus c square root b is an irrational zero of the polynomial, then so is a minus c square root b. And I also have the restatement of the non-real zero. So basically, the same thing. So the examples you're going to primarily be given and expected to do on the test are all going to have rational coefficients. As a matter of fact, more times than not, they're probably going to be integer coefficients, which makes them rational, which makes them real, and therefore it's going to obey these rules. So some things to be on the lookout for is that if I have an irrational zero, then its conjugate should also be a part of that. If I have a non-real zero, then I know that its conjugate should also be a zero. And so this helps me to establish additional information along the way. So let's have a look at how we can make use of these things. And also along with this, because irrational zeros have to come in pairs, and because non-real zeros have to come in pairs in the circumstances that you're going to be given. If it's an odd degree polynomial, because the irrationals and non-reals have to come in pairs, then if it's an odd degree polynomial, you should definitely have one rational zero. So this is very important for the circumstance. Now again, this has to deal with a situation where I have rational coefficients. We want to find a polynomial function with rational coefficients of the lowest possible degree with the following zeros. Okay, so we know that we have 2 as a 0, -3 as a 0, 5i as a 0, and square root 11 as a 0. Based on the rules, and this says it has to be one that has rational coefficients, I know that I have two other zeros here. -5i is going to be a 0 because that's the conjugate of this one. And negative square root 11 is going to be a 0 because it's the conjugate of this. So there's two more zeros that I automatically have to have because I know it's a polynomial function with rational coefficients. Now I have to try to figure out what this polynomial is going to be. And I'm going to be doing a lot of foiling and multiplying and so forth. For it to be having the lowest possible degree, these would be the only zeros I'd expect. I mean, I could come up with other zeros to just make up a zero. It also has a 0 at 7. But I'd be adding extra zeros and therefore adding more factors, which means I'm raising the degree of the polynomial. So for it to be the lowest possible degree, I'm going to just assume that these are the only zeros, which means that this polynomial function, which I'm just going to call f of x, is going to have, well, since 2 is a 0, x minus 2 is a factor. Since -3 is a 0, x minus -3 would be a factor, which means x minus -3 becomes x plus 3. Since 5i is a 0, that means x minus 5i would be a factor. And we already established that -5i had to be it as well, so x minus a -5i, which become x plus 5i, is also a factor. Square root 11 is a 0, so x minus square root 11 would be a factor. And since negative square root 11 was also a 0 because it's a conjugate, x minus square root 11, which would become x plus square root 11, is also a factor. So now what I'm going to do is get some foiling going on, some multiplication and distribution going on here. So I'm going to do these two together because they're conjugates. The same thing with these. The fact that they're conjugates makes it a little nicer multiplication, because if they're conjugates, going back to what we talked about with conjugates before, in conjugates, when I have the same two terms just separated by a different sign, when I do the foiling process, the O and I part, the outside and inside portions, cancel. So I can actually take a shortcut and say, well, these is going to be x times x, which is x squared, negative 5i times positive 5i is a minus 25i squared, which is not something we would tend to write it in that format. So I could say that that's going to be x squared plus 25 because I squared is -1. And likewise with this, the O and the I part of the foiling process will cancel out. X times x is x squared. Negative square root 11 times positive square root 11 is going to give me a minus 11. If I multiply x minus 2 times x plus 3 through, I'm going to have x squared plus 3x minus 2x minus 6, which becomes x squared plus x minus 6. This one has 3 terms in it. The other ones have 2 terms. So I'm going to multiply these two together next because it's a little bit easier at that point. So I can rewrite f of x as x squared plus x minus 6. x squared times x squared is x to the fourth. X squared times a negative 11 is a minus 11x squared. 25 times x squared is a plus 25x squared. And 25 times a negative 11 is going to give me a minus 275. And so if I can combine some like terms on that one. And then lastly, I'm going to have to distribute one last time to get this final expression. Which means I'm going to do x squared times x to the fourth, which is x to the sixth. X squared times 14x squared, which will give me a 14 x to the fourth. X squared times a negative 275 is a minus 275 x squared. No, that takes care of this one. The x's, I'm going to say x times x to the fourth is going to give me an x to the fifth. X times 14x squared is going to give me a 14x cubed. The x times a negative 275 is going to give me a minus 275x. And then lastly, negative 6 times x to the fourth gives me a minus 6x to the fourth. It's the same procedure we often use for foiling. Negative 6 times 14x squared. It's going to give me a minus 84x squared. It's just that you have to just make sure you're keeping track of which quantity in the first one are you multiplying to the quantity in the second one. And negative 6 times a negative 275 is going to be a plus 1650. And then I look to combine some like terms. And I want to write this in standard form. So as I combine these like terms, I'm going to want to make sure that, I start with the highest power and work my way down. So x to the 6 was like it's the highest power up here. X to the 6 is the only term that has it. So I'm going to write x to the 6, which means I kind of took care of this one. The next one I have is x to the 5th. I only have one term with x to the 5th in it. That's this one. So plus x to the 5th. X to the 4th will come next. I have 14x to the 4th minus 6x to the 4th. So I'm going to have plus 8x to the 4th. Takes care of these two. The x cubed would come next. I do have a 14x cubed and only one x cubed term. Takes care of this one. X squareds would come next. I have a negative 275 x squared minus an 84 x squared, which means that I would have a negative 359 x squared. X terms are next. I only have a minus 275x. And then constant term plus 1650. So this would be one possibility. The other possibilities would just be multiples of this. I should expect to have a 6-degree polynomial because I've been able to define having 6 zeros. Anything beyond this, I would be multiplying this by a single constant, and therefore I could have variations on that and have different maximums and minimums as a result of that, but ultimately this would be the main function and the other ones would be multiples of this function. So that's kind of lengthy and there's a lot of multiplication going on, but they do ask questions like this, maybe not as severe. I'm trying to give examples that have the non-real and irrationals in them, whereas they may give you a lot of ones that have one or the other, just not both. Now, another thing that we can use to help us identify rational zeros is called the rational zero or rational root theorem. So let's have a look at that rule. The rational zeros theorem, which is also known as the rational root theorem, sometimes it's known as the rational root test. If you're given a polynomial where all the coefficients are integers, so which is generally what we're going to be facing in most of the examples you're going to be given. So they're all integers. If p is a prime factor of a sub 0, And Q, now again, they're not assuming this P out here. They're assuming this is a different constant. They probably should have put this in terms of F to make it more clear. I don't want you getting confused that this P and this P are this represent the same thing. They don't. Okay. We let P be a prime factor of A sub 0, which means A sub 0 is the constant term. And Q is a factor of A sub n. A sub n is the leading coefficient. Then any rational zero of f of x would be of the form P divided by Q. This used to be a big deal before the dawning of calculators and other things that, are used typically today. The reason being is typically if, a mathematician was looking to find the zeros of a polynomial and looking at the one we have in example 2, we could say, okay, I expect up to 4 zeros here. So let's just try to plug some numbers in and find them. Now, first of all, I don't even know if it has any rational zeros. This thing has an odd number of terms, so I'm not going to be able to group and factor or use any other techniques that we're familiar with as far as factoring goes. There are methods taught in some older textbooks which teach you how to split middle terms, but that's a lot of trial and error. And even with that, those factoring methods don't necessarily work nicely if you have irrational numbers as solutions. So they would basically be left with no choice than to go through and just kind of list numbers, try them out until they are able to find some. Now, if you follow that, you can say, okay, well, this one's getting closer to 0. I'm on the right track. If I say I'm going to go from 2 to 3 and it's getting further away from 0, then I'm saying, okay, well, maybe I'll go in the other direction, maybe try out 1, -1, zeros, any of that stuff to see if those work, and then maybe try some fractions. But the fact of the matter that you have so many different fractions involved, if I find out by the intermediate value theorem, hey, this one has an answer between 1 and 2. There's a lot of fractions between 1 and 2, like 1.1, 1.5, 1.05. There's a whole bunch of different things that, are rational that could possibly have zeros. So basically, they were stuck with having to go through quite a large number, basically an infinite number of possibilities. This at least broke it down into a tangible, finite list of numbers to try out. Here's how it works. So I'm looking at the leading coefficient and I'm looking at the constant term. So one thing I definitely want to do if I'm going to be using the rational zero theorem in any shape, form, or manner, and usually if I'm looking to find zeros or I'm looking to graph the function, I should probably have it in standard form anyway. Q are the prime factors of the leading coefficient. So I got to think, well, what integers go into 2? Well, it's not a whole extensive list. I have plus or minus 1 or plus or minus 2. Those are the factors. The factors known as P, well, what numbers multiply to give me a -15? Or what numbers can I divide into and get no remainder? Well, plus or minus 1, plus or minus 2, no, plus or minus 3 would, plus or minus 5, or plus or minus 15. That's my list. Now, the possible rational roots, or zeros. I just take every possibility of P divided by Q. So 1 divided by 1 would be plus or minus 1. 3 divided by 1 would be plus or minus 3. 5 divided by 1 would be plus or minus 5. 15 divided by 1 would be plus or minus 15. Plus or minus 1 divided by plus or minus 2 would give me plus or minus 1/2. Plus or minus 3 divided by plus or minus 2 would give me plus or minus 3/2. Plus or minus 5 divided by plus or minus 2 is plus or minus 5/2, also known as 2.5. And plus or minus 15 divided by plus or minus 2 is plus or minus 15/2, which would be plus or minus 7.5. So even though I have an infinite number of possibilities, before this, I applied this theorem, now I have this whittled down into 2, 4, 6, 8, 10, 12, 14, 16 possibilities. So if you're going from an infinite number of possibilities down to 16, that's a big deal. Now, with the dawning of calculators and things like that, and using graphing techniques more often, it's a little easier nowadays. I could certainly use other things to much more quickly identify what the rational zeros are. Now, this list of possible rational zeros are only possibilities. Remember, this thing only has 4 zeros. I'm listing 16 numbers as potential zeros. Obviously, all of them are not going to be zeros. Some of them are expected to be zeros, and that's only if I do have rational zeros. I may not. This would be the list I could choose from to go through, plug this into the polynomial, and see if I do in fact get 0. And that's something that you could use to benefit you. Again, with the calculator, how do we use this nowadays? Because ultimately the calculator, I can identify what the zeros are. Okay? I could graph it on my calculator, use the calc feature, have it find zeros for me, and then find that. But sometimes the decimals I get as reports are a little bit off because it uses a version of the intermediate value theorem to kind of zoom in and hone in on a number. And once it gets close enough, it says, okay, that's the 0. So if I'm looking at a number, and say I graph this, and I saw something along the lines of 2.49998876 as an answer. Well, I'm thinking, well, that looks like it's about 2.5. Is 2.5 a possibility here? Well, from my list of rational roots, yeah, it is. It's worth something to try out. It looks like it might be irrational because I don't see any kind of set repeating pattern, but it could just be reporting that way on my calculator because of the way it comes up with the answer. So what we could use it nowadays for is I can look at this and I can focus just my attention on that leading coefficient and say, well, since the only numbers that go into that leading number are 2 and 1, any answers I would get that are rational should be integers, or they should be halves, which means I should see 0.5s. And I also could reduce it and say, okay, well, the integers should be multiples of 15. And so if I say, well, is 12 going to be a possible answer? Well, no. If it looks like the graph is passing through at 12, no, I don't expect that to be an answer. So it's probably not going to be 12 exactly. It's going to be 12 point something or other, and it's probably going to be irrational. Or it means I didn't graph it right to begin with. So the rational zero theorem is used a little differently nowadays since the calculators can aid us. As I mentioned here, this is a tedious process, but you can then figure out that f of 1 is 0 and f of negative 3 halves is 0. So on my list, I end up finding out that the only rational ones that actually are zeros are 1 and negative 3 halves, which were the actual zeros. 3 halves. The rest of the possibilities weren't zeros. Once you establish those, well, I want to find the rest of the zeros. You notice when I look at the graph of the function, it looks like just a parabola. And no matter how far out I go, I don't see any more turning around. And it doesn't take me long to come to that conclusion because it is a degree 4. I do expect the two ends to be pointed in the same direction, ultimately, so they are. I don't expect any more turning around at any other point. I do expect to see 4 zeros. I've established 2 of them which are rational, but chances are the other 2 are going to probably be non-real, and they're not going to show up on the graph ever. How do I find out what those are? Well, that goes back to the techniques we were talking about beforehand. I've established the rational zeros. Let's find the rest of them. So I'm going to go back and rewrite my function. And by using the rational zero theorem, and with help of the calculator as well, I've established that x equals 1 and x equals negative 3 halves are zeros. I want to find the rest. So I want to find ones that are rational. Either they're irrational, which unlikely, I'm not seeing them show up on the graph, or they're going to be non-real. So, and chances are I'm going to expect them to be non-real because I'm not seeing any other ones show up on the graph. But I do know at least with if I factor out the factors that go along with these two zeros, I'm going to be going from a degree 4 down to a degree 2, which is quadratic, and I can handle that using other methods. So let's do it with that. So I want to break down that f of x further. So I'm going to use synthetic division to break it down because I now know that x minus 1 and x plus 3 halves are factors. And again, that comes from the factor theorem and just putting an x minus in front of these two zeros. I use the zeros though for my division because I'm going to use synthetic division. So I'm going to rewrite the coefficients. I have a 2x to the fourth, a 1x cubed, a 7x squared, a 5x, and a minus 15. So no missing x terms. And I'm going to do the 1 first. Doesn't matter which one I do first. So basically this division is going to factor out the x minus 1. So I'm going to bring down the 2, multiply by the 1, I get a 2 here, add, I get 3, multiply by 1, I get 3, add, I get 10, 1 times 10 is 10, add those, I get 15, 1 times 15 is 15, negative 15 plus 15 is 0, which, that's what I expect it to be. Now, I'm not going to stop my division here, because if I stop my division here, this basically would let me say at this point that f of x equals x minus 1 times 2x cubed plus 3x squared plus 10x plus 15. I want to break that down further because I know there's another factor. That one. And it doesn't look like there was any multiplicities when I was doing that either, so I don't have to, if I saw a multiplicity on one, I would probably try to factor it again and see if it indeed was. But, I didn't see any evidence of that. I didn't see any flattening. I didn't see it just touching at one and moving on. So we're good. All I'm going to do now is, I've taken care of this one. I want to now take care of this one. So I'm just going to start with this list of coefficients again and divide by the negative 3 halves. Bring down to 2. Negative 3 halves times 2 is a negative 3. Add those, I get nothing. Negative 3 halves times 0 is 0. Plus 10 is 10. Negative 3 halves times 10 is a negative 15, which gives me a 0. So now what this means is that I've broken this down even further now. The x minus 1 is gone, because I did that in the previous step. The x minus negative 3 halves, which is x plus 3 halves, is now factored out. And what I'm left with is, well, this is my remainder, this is my constant term, this is my x term, this is my x squared term. So I have 2x squared plus 10. So I have this factored, and remember, I'm still looking for the zeros. Well, obviously, by the zero product rule, either x minus 1 equals 0, which of course gives us the x equaling 1 again. That part's repetitive. I already knew that was a 0. I didn't really need to reestablish that. Same thing with this. X plus 3 halves is a 0. Again, that gives me the x equals negative 3 halves, which I already established was a 0 from use of the rational zero theorem and also making use of the calculator to a certain extent. It's this one I was mainly focusing my attention on, the 2x squared plus 10 equaling 0. if that equals 0, that would also produce a 0 of the polynomial. So I'm going to subtract 10 from both sides. I'm going to divide both sides by 2. And then I'm going to square root both sides. And I'm going to put the plus or minus symbol over here. But when I square root a negative, that goes along with saying that I'm going to put that I on the outside. And that represents my two non-real zeros. So if I wanted to state at the end here, my zeros are x, and I'm just going to write it as a list. I have negative 3/2. I have 1. I have I square root 5. And I have negative I square root 5. That's a list of 4 zeros, which is how many I expect. That's my solution set. There's one other rule that we're going to look at to aid us a little bit, although again, it's a rule that has a little bit of use, but it's not necessarily a huge use. I mean, it does help us establish some things along the way, and that's called Descartes' rules of signs. So let's have a look at that. So for Descartes' rules of signs, this is another thing to help me determine how many zeros I could expect. I mean, we had the rational zero theorem which said, okay, we can expect this many rational zeros. These are possible rational zeros. And we had a list that we could try and see if there are them. Descartes' rules of signs deals with helping us determine how many positive real zeros and negative real zeros that we could come up with. This helps us establish the real zeros so that we can say, okay, well, if we're getting this, then we can expect maybe some non-real zeros along the way. It's saying that let P of x be a polynomial with real coefficients written with the powers of the roots in descending order or ascending order. So basically, I mean, if we write this in standard form, we're good. The number of positive real zeros of P of x is either equal to the number of variations in signs in P of x, or equal to the number of variations in signs in P of x minus an even integer. Now, what that means is if I have all of the x's, the powers of x is represented, again, I don't have to worry about any zeros because those don't consider changes in sign. All I'm looking is that the signs to see if they change or anything in between them. That's going to help me figure out the possible number of positive real zeros I could get, and negative real zeros. I'm just going to take the polynomial function, replace it with negative x, simplify that, and then compare the sign changes and make a very similar determination. So with A, when I look at f of x, now I have a 4 that's positive, so it goes from a positive term to a negative. That's one sign change. Then it goes from a negative to a positive. That's another sign change. So I'm up to 2 sign changes. When I go from the 7x cubed to the 2x squared, there's no sign change. So right now I have 2 sign changes. I then go to a minus 8x. That's a third sign change. And then I go to the plus 1, which is a fourth sign change. So f of x had 4 changes in sign. That means the number of positive real zeros is going to be either 4 or that number minus an even integer. So if I subtract 2, I can have 2. If I subtract another 2, or none. So I could either have 4 positive real zeros, 2 positive real zeros, or none. One of these has to be true. I then look at f of negative x. Negative x raised to the 5th power is a negative x to the 5th, and times 4 is going to be a negative 4x to the 5th power. Negative x to the 4th is a positive x to the 4th, times a negative 6 is going to be a minus 6x to the fourth. And I keep doing the simplification. So f of negative x has now been established and simplified. And now I look at the variation, the sign changes in this. I go from a negative 4x to the fifth to a negative 6x to the fourth, no sign change. Going from the next term, no sign change. Going from the negative 7x to the third to the 2x to the squared, there's a sign change, so I have one sign change. And then the rest of them are positive. So here, I have one sign change. So the number of negative real zeros is 1, and that's it. Because if I try to subtract an even integer from that, I'm going to get negative. I can't have negative. I can't say, well, I have negative 3 negative zeros. That doesn't make sense, So this pretty much tells me that this function here is going to have one negative real zero. So I know it's guaranteed to have one real zero. Okay? It's a fifth degree polynomial, so it could possibly have 4 others that are positive. It could have 2 others that are positive, which means I would probably have another 2 that are non-real. Or I can have none that are real, or positive and real. That means that the rest would have to be non-real. So again, this kind of thing can help me figure out what kind of answers to expect. Because if I come up with an answer and I come up and say, oh, 2 of the zeros for this, are negative 3 and negative 6. Well, that's impossible, because this should only have one negative real zero. For B, let's start with f of x. For f of x, I start with, now these are written in order. I don't have to have zeros between them. I'm good. So I have a negative 9x to the seventh to a 4x to the fifth. That's one change in sign, to a positive, to a positive, to a negative. So I have 2 sign changes. That means that I have, as far as a possible number, of positive reals, I have 2 or I have none. Now I'm going to do f of negative x. And as a shortcut, anything that has an odd degree is going to have a sign change when I do f of negative x. Hopefully you've noticed that now. So anything that has a odd exponent on the x is going to have a sign change. So this is going to become a positive 9x to the seventh. This is going to become a minus 4x to the fifth. The x squared is going to stay the same. The 9x is going to have a sign change because that's an odd power. And of course, the minus 2 has no x on it, so changing it to a negative x won't do anything. And now I see that I have 1, 2, 3 sign changes. And therefore, when I look at the possible number of negative real zeros, I could have 3 of them. I can subtract an even integer of 2, which can be or 1 of them. And if I subtract 2 from that 1, that's going to be negative. So I'm either going to have 3 of them or I'm going to have 1, which means I'm guaranteed to have at least one negative real zero on this. So if I don't come up with a negative real zero on this, I'm doing something wrong. Now again, this particular rule here doesn't really help me establish what they are, but it does let me know what I can expect as possibilities, which in the end can help me zero in on an answer. Now for example 4, this is a lengthy video here, and this last part is going to be quite involved because I'm going to incorporate a little bit of everything we've learned so far in this chapter into this. So let's have a look at example 4 and go from there. So for example 4, you're given this 7th degree polynomial function. Sorry about the big wonky plus sign there, but there was a sign error that I noticed when I made the slide. I fixed in the notes, but didn't fix it here until there. I'm being told that the x equals 2 plus the square root of 3 is a 0 of f of x. I'm asked to find the remaining zeros. So a couple things I know about this function based off of the rules we've established so far, and I'm going to list them right here. First, based on the degree of the polynomial, I expect to see 7 zeros. Now, I don't know if those zeros are going to be all real. They're going to be rational, irrational. I don't know if, anything beyond that at this point. If any of them are going to count more than once and have a multiplicity, I have to wait to see more, do more detailed work into this function to find out more information. But I do know I expect to have 7 zeros, one of which was given to us already. So there's 6 more I have to find. I know the end behavior, it's going to look like that. Because it has an odd degree, and I know that any non-real zeros have to come in pairs because all these are integer coefficients, which makes them rational. And since I know that any irrational zeros have to come in pairs, that means I have to have at least one rational zero. Some other information I can deduce from this. If I'm going with Descartes' rules of sign here, f of x has 1, 2, 3, 4, let me take that back. 1, 2, 3, 4, 5, 6 sign changes. Which means I can expect to have either 6 of them, 4 of them, or none of them. F of negative x, which is basically going to be, having this is a negative, this is a positive, that would still be negative. Although all the odd ones are going to change sign. This is going to be negative, that's going to remain negative, that's going to be negative, that's going to be positive, that's going to become positive, that's going to stay positive. So basically I'm going to have one sign change. Now if you want to verify and plug the negative x in and make sure of that, but it has one sign change, which means I'm going to have one possible negative real zero. So that's a sign that I'm going to have at least one real one. Now, is that going to be my one rational zero? I don't know. I actually have no positive real zeros, but I know I have to have one that's negative real zero, and it could be my rational zero too. So there could be some movement between these two, but I just want to make sure that I verify that as I go along. Now, the fact of the matter is, I know that I already have one positive real zero because 2 plus square root 3 is one of them. So I know I know zero's out up down over here. So I'm gonna probably have to have at least at least 3 other possible real zeros as well. So again, this helps me figure out what kind of answers to expect. And the last thing I can look at when I look at my rational zero theorem, my rational zeros, because the leading coefficient's a 2, 270 has a lot of factors. So me listing all the possible factors it'd be quite a lengthy list. But because the leading coefficient is 2, I would expect to either have integers or something of the format where I have a number, a decimal point, and a 0.5 because I'm dividing by 2. Those are other things I'm looking at. So that's a lot of information so far. It doesn't actually zero in on what any of the zeros are, at least the other 6 I'm looking for, but at least I know some things about this that will help me stay away from, other, pitfalls. Now, what I also chose to do at this point is I did a quick graph. Now, you're not going to be given many of these that are degree 7. I wanted to include one that had a little bit of everything in it. A lot of the ones you're going to deal with aren't going to have all the aspects, all the types of zeros, and have multiplicities, and some of them are going to have maybe have a multiplicity but have no non-real zeros. Some of them may have, you know, some irrational zeros, but the rest will be rational, and they have no multiplicities. There's going to be different variations of them. They're not going to have all the characteristics in all of them either. So I'm just trying to pick one that kind of talk about all the talking points so you can see that. So don't expect everything to be quite this complicated. I just want to make sure I picked an example that had, a little bit of everything in it so we can kind of show how we can incorporate everything we know. When I did a quick graph of this on my calculator, and I'm not going to go into like the minimums, maximums, and the settings I put on it. The graph I got this is an integer, 3. 3 is a factor of 270. So by, again, going back to the rational zero test, that is definitely a possibility. Negative 1.5, which is 3 halves, is also, if 3 is a factor of 270, so is 270 of the 270 over 2, and so is negative 1.5. So, those are both possibilities by the rational zero test, so those are good contenders. I also see right here that at x equals 3, the graph is touching the x-axis but not passing through, which indicates this has a multiplicity of 2. That means when I count x equals 3 as a 0, I count it twice. So on the right hand side, my positive real zeros, I have 1, 2, 3, 4, which is definitely a possibility here. And as far as possible negative real zeros, well, this one is my negative real zero. I know I had at least one rational zero possible, but I have 2 here, so I did meet that category. I know this is a complete enough graph because it's obeying this. 7 zeros. Right now I'm accounting for 1, 2, 3, 4, 5 of them. I know that chances are I'm not seeing any signs that I'm going to have 6 positive real zeros here. That means there's 2 that are not accounted for. And because the end behavior is acting the way it should be, I'm going to probably expect that the other 2, I'm going to have 2 of these that are non-real. Along with that, now that's what I'm going to be ultimately looking for on this. I'm going to be trying to locate and find out the value of these 2 non-real ones because I've already established most of the other ones because this my calculator gave me, this my calculator gave me. This one is irrational, but this also happens to be what 2 plus the square root of 3 is. Because that was told to me that was a 0. But because this is, my original function was f of x had, integer coefficients, which means that they're all real number coefficients, they're also all rational, that if 2 plus square root 3 is a factor, or a 0, 2 minus square root 3 is also a factor, and that's what this one would be. So I know what all of my real zeros are at this point based on the information I was given in the problem and the graphing and the analysis I did. What I have to do now is figure out what those 2 non-real zeros are. And that's where most of the rest of the work's going to be, just to find those 2 other zeros. So right now I've established 4 other zeros. I have 2 minus the square root of 3. I have negative 1.5, or negative 3 halves. And I have 3, which counts twice, because it has a multiplicity of 2. There's 2 other zeros I got to find. So what I'm going to need to do is use what I've found thus far and take that f of x and factor it down so I can find what those 2 non-reals are. And I'm going to do that in using 2 different other facts. So let's give myself a little bit more room. Well, what I need to do is go, now having the zeros, I got to figure out what my factors are. So my factors of f of x. I'm going to have x minus a negative 3 halves, which is x plus 3 halves. That gives me the x equals negative 1.5 as my 0. I'm going to have x minus 3 as a factor. I'm going to put a little square on that to indicate it has a multiplicity of 2. I have an x minus 2 plus the square root of 3 and x minus 2 minus the square root of 3. Those would give me the 2 minus square root 3 and the 2 plus square root 3 as my other zeros respectively. I need to divide these out of f of x, because if I do that, that's going to take my degree 7 polynomial. These will account for 5 of those degrees. What I will be left with once I factor these out is another second degree polynomial, which I can certainly find the zeros for, and those zeros are going to be the ones that are more than likely the non-real ones. So how am I going to do that? Well, these, since they are essentially my situations where I have a linear binomial with a leading coefficient of 1, I could do synthetic division with these. These, on the other hand, they're not synthetic friendly. So chances, and that's because, like, I mean, I could try that, but I'm going to have a lot of irrational numbers along the way trying to deal with it. It's not going to work out very nicely. It's going to be really clunky, and I really don't want to have to use synthetic division with those. So, but what I can do with those is multiply them together. So if I take x minus 2 plus the square root of 3 and x minus 2 minus the square root of 3, and I multiply those through, I'm going to have x squared minus 2x minus x square root 3 minus 2x plus 4 plus 2 square root 3 plus x square root 3 minus 2 square root 3 minus 3. So if I take each term of the first quantity and multiply it to each term of the second and multiply it out, I would get these. When I combine some like terms, I have x squared minus 2x minus another 2x is a minus 4x. The negative x square root 3 and the positive 1 cancel. I have a plus 4 and a minus 3, that's a minus 1. The 2 square root 3 and the minus 2 square root 3 cancel. So I have this. So I now can say, well, now this is a factor. And this I will eventually long divide. Because I can only do synthetic division with linear binomials with leading coefficients of 1. This is no longer that, but it would be probably a lot easier to use this than to use the linear binomials that happen to have irrational numbers as part of them. Now, which order do I want to do these? Do I want to do the synthetic divisions first and then the long division, or vice versa? In the end, it really doesn't matter. They should, I mean, each time I factor one of these out and carry through the division, I should get a remainder of 0. I should get a nice polynomial expression that is my quotient. However, I could save myself a little work if I do the synthetic first, because again, with long division, the bigger the difference between the degrees of the two things I'm dividing, the more steps it takes. If I started by doing my original polynomial, which is a 7th degree polynomial, and dividing by this square polynomial factor, it's going to take a number of steps to do it. Whereas if I factor out these three factors, including the three twice, with synthetic, I'll be down to a degree 4 polynomial. And when I divide that by a degree 2 polynomial, that's far less steps. So that's the route I'm going to take with this, and that's what I'm going to use. Um, so let's go with that. Give myself a little bit more room. So I'm going to go back to my original function. I'm not going to rewrite it here because I have it in front of me. You'll have it on your paper. I'm going to rewrite the coefficients. So I'm going to say, okay, I'm going to have, and I'm going to carry through the synthetic division. Now it doesn't matter which order I do them in. I'm going to take care of the 2 3s first. I'm going to do one synthetic division with 3. So that's the first synthetic division of 3. This would be a 6th-degree polynomial if I decided to write it out, but I'm not going to bother with that because I really don't want that 6th-degree polynomial is no use to me. Let's break it down further. I'm going to carry through another synthetic division of 3. Again, this really is no use of me yet because I still have another linear binomial, so now I'm going to use the negative 3 halves. But right now, taking care of these guys, I can now say with the synthetic division that f of x is now x plus 3 halves x minus 3 squared times, now again, going with it, this is now should be a 5th-degree polynomial. So I'm going to have 2x to the 5th. Maybe it's 4th. Let's see, 1x squared. Yeah, it's x to the 4th minus 12x cubed plus 38x squared minus 84x plus 20. Okay, so now I have this. This is now what I'm going to be dividing by this quadratic factor. Now I'm going to do my long division. So now I'm going to set up my long division. Now again, I'm not going to talk step by step through the long division process. We've already talked about long division. I'm just going to carry it through so you can see what you would get, but certainly you should practice this as well. So I'm just going to do the work and then resume talking. So I got my remainder of 0, and I now have this broken down even further. So now I can rewrite f of x I still have the x plus 3 halves, the x minus 3 squared. Scooch this over a little bit. I now have the factor 2x squared minus 4x plus 20, which is what the quotient was. And that's because I factored out the x squared minus 4x plus 1. So that's the factored form. Now it's all linears and quadratics. The thing is, I don't have to worry about this because this is what gives me the negative 3 halves as a 0. I already know that. I don't have to worry about that. This gives me my x equals 3 as a 0. I already know that. This is what I factored out through the division here. I already knew that was a factor, and the two roots I got from it are the 2 plus square root of 3 and 2 minus square root of 3. With this equal to 0, what I'm really just concerned about is this one. This is the one that's going to give me my non-real zeros. So 2x squared minus 4x plus 20 is set equal to 0. Everything's divisible by 2, so it makes my life a little easier if I just divide everything by 2. I'm not even going to try doing anything but the quadratic formula. I mean, factoring, it's not going to work because I already established that this is going to probably be where my non-real zeros are from. I just did it ahead of time, so I'm not going to use a strategy that doesn't work with it. Completing a square, again, is usually a version that people don't like, so I'm just going to go and use the quadratic formula on this, and that's going to give me, which simplified further becomes, which is finally. So now I've established all of the other zeros. So I'm going to go back up and answer the question now. Find the remaining zeros. I don't want to move that. So the remaining zeros are 2 minus the square root of 3, negative 3 halves, 3. I don't have to list it twice, but I might want to indicate it has a multiplicity of 2. I have 1 plus 3i, and I have 1 minus 3i. So that's a grand total of 1, 2, 3, 4, 5, 6. 6 additional zeros that are given for degree 7, and I was already given 1. So everything's accounted for. That's the solution. So very intense work on this one. You're not going to usually be given something this intense. Again, I just wanted to pull an example out where a little bit of everything had to be used, so you could see it all in action. Because it's possible, but you're not going to probably be presented with many instances where that has to be done. So, but use what you learned here. Practice some other functions from your textbook. Ask any questions you have in class, or come and see me during office hours to get some additional help. Until I see you in class or in office hours, or until the next video, I'm going to bid you good day, and I'll see you around. Bye, everybody.